Good day. Welcome to another session for our mathematics live class. Now, in our earlier sessions, we have been looking at some interesting concepts. In our last session, in particular, we looked at the concept of geometric progression. And for geometric progression, we consider the fact that they are simply sequences where their terms increase by the use of a common ratio. We talked about the fact that for a geometric progression, if you have your first term, to get the next term, all you just have to do is multiply this first term with the common ratio, like so. And then you could generate the third term by multiplying the common ratio again with the second term, and the process continues, right? We also looked at various formulas we could talk about as far as the geometric progression is concerned. We talked about the fact that the nth term of a sequence of this geometric sequence is in fact a r raised by n minus 1. And then if you were to take the series form of this progression, which means adding the terms together, like a plus ar squared and continues, then you could generate the sums of this geometric progression, or we call them the geometric series, by taking note of what the common ratio is. If the common ratio is less than 1, then we will simply say that the sum of the first n terms is equal to a into 1 minus r raised by n divided by 1 minus r. If we have that the common ratio is greater than 1, then the sum of the first n terms will simply be a into r raised by n minus 1 divided by r minus 1. And then we took a special case of when the common ratio is less than 1, that is the absolute value of the common ratio is less than 1, and we are kind of finding the sum to the infinity of their geometric series. That is, if the absolute value of the common ratio is less than 1, of course, this means that we are saying that the ratio itself is between minus 1 and 1, then we can find the sum to infinity as a divided by 1 minus r. We also looked at ways in which we could generate this from the normal sum and various examples as regards using the formulas for geometric progression and the geometric series. For today, we are now going to be looking at operations in a generalized form, right? Now, we are very, very familiar with how we use our basic arithmetic operators. When we say arithmetic operators, we are talking about the plus, the minus, the times, and of course, the division, right? We are very, very familiar with how we use them. We know what happens when we do 2 plus 3, that's 5. We know what happens when we do 3 minus 1, that's 2. We know what happens when we do 5 times 4, that's 20. We know what happens when we do 20 divided by 4, that's 5. However, these are just normal arithmetic case where we have them as normal numbers. When I say normal numbers, I'm talking about the normal counting numbers or the set of integers as the case might be. However, we can also consider operations happening in a generalized form. When I say generalized form, when we are now talking about operators that revolve in a form greater than these mathematical operators or these arithmetic operators. How then can we define those operations? How then can we carry out various combination operations with those particular operators? This brings us into our topic for today's live class. We will be treating the concept of binary operations. Now, for binary operations, the very first thing that we have to keep note of is the fact that we cannot solve them without a very, very good understanding of how the normal arithmetic operations work. So binary operations are hugely dependent on our normal arithmetic operation. That's one. The second thing we have to know is the fact that the binary operators can be expressed by any and every kind of symbol. A binary operator can be expressed by any or every kind of symbol. Now, what makes it a binary operation? What now makes it a binary operation is the presence of this particular definition for that binary operator. So let's list out some stuff. First, we have said it is dependent on the arithmetic operators. So we are talking about the plus, the times, the subtraction, and the division. We have also said that can be expressed as symbols. However, those symbols become the binary operator only when they are armed or equipped with a definition. Right? So for any kind of symbol we have, any kind of symbol at all, what now makes that symbol a complete binary operator is the presence of that definition. And it's not far-fetched. Even for our normal arithmetic operations, there are underlying definitions that allow them to act. When you do 2 plus 3, the underlying definition of the plus sign is the fact that you are taking the entirety of 2 and you are adding it to the entirety of 3. That's why in elementary classes you have them count. You say 2, you have 1, 2, then you count 3, 1, 2, 3, and then you count them all together. 1, 2, 3, 4, 5. And then you see that 2 plus 3 is equal to 5. Because the underlying definition for the plus sign is the fact that you are combining the totality of both sides. Similarly, if you take the subtraction sign, which is this, then you are combining the underlying definition of take away. So if you are doing 3 minus 1, then you are saying that you are taking away 1 from 3. That is the underlying definition there. Right? So every single operator, whether it is binary or it's an arithmetic operator, every single operator has its own underlying definition. The reason why we do not take note of those definitions for this is because they are definitions that has been ingrained into us from elementary. Ever since we have started dealing with numbers from our primary 2 or thereabouts, we have been dealing with these operators and their definitions. So they come to us so regularly that we do not even take note of them. We just apply them as they come. However, for this binary operation, each and every single time a symbol is quoted to be a binary operator, then we have to denote the symbol by its definition. What does that mean? It means that we will not be able to solve a question under binary operation unless, of course, you are getting the definition for that binary operator. That is the most important thing. Before you can attempt to solve a binary operation question, you must be given the definition of that binary operator. That is the first most important step. Once you now have that binary operation definition, then you can now proceed to see how they want you to carry out the operation between whatever variable you are given. Now, the definition of this binary operation is that fact that is completely dependent on that arithmetic variable or the arithmetic operations. Do you understand? So when we say the binary operation is hugely dependent on the arithmetic operators, what is in fact very, very dependent is that definition. Let's take an example. So, for instance, we can let asterisk. Now, we are saying asterisk now is our symbol. Be a binary operation or a binary operator, whichever one you decide. However, if asterisk is a binary operator, it has no use for us. We do not know how to deal with asterisk as a binary operator until it has been defined. So let asterisk be a binary operator defined by, now this is where the beauty comes in. Defined by, let's take A asterisk B, which means when we operate A and B under that asterisk binary operator, what do we expect to get? What we expect to get is where the dependence of the arithmetic operator comes in. So we can say that A asterisk B can be defined as A plus B minus 2, for instance. You will see that on the right hand side, all we have a combination of arithmetic operators that we know their basic usage. You know what it means to add. You know what it means to subtract. This is where that dependence comes in. The binary operator is dependent on the arithmetic operators in order to have significance. And without this definition, so this entire line is what we refer to as the definition of a binary operator. This definition is what allows the binary operator to actually act and operate. So if you say A asterisk B is equal to A plus B minus 2, then we are saying that whenever you operate A and B with respect to the binary operator asterisk, what I'm expecting you to do is add A and B together, subtract 2 from them. This is the definition of the binary operator. So for instance, if I were to take 3 asterisk 5, then the result for this will simply be 3 plus 5 minus 2. 3 plus 5 gives you 8, minus 2 is equal to 6. So it means that 3 asterisk 5 is equal to 6. You would see that there is no way we would have known that 3 asterisk 5 will give us 6 if we did not have the definition of the function or of the binary operator. Asterisk is not the only symbol you can use. Any symbol can be used, provided that you are accompanying that symbol with its definition. For instance, if we say let not be a binary operation defined as C naught D is equal to C minus D divided by C plus D, then this is the binary operator, not is the binary operator, and this line is the definition for how the binary operator is used. Of course, you know that anytime we operate, even with our arithmetic operators, you can only operate 2 terms at once. When you do 2 plus 3, it is 2 and 3 that are the 2 terms. Even if you have 2 plus 3 plus 7, you must first find the result of 2 plus 3 first before adding 7 to it. Or find the result of 3 plus 7 first before adding 2 to it. So each operator takes the operation with 2 terms at once. That is why we are defining it this way. So if C naught D is defined as C minus D divided by C plus D, that means that if I decide to take 7 naught 3, then according to its definition of that binary operator, this would be equal to 7 minus 3 divided by 7 plus 3. This will give us 4 divided by 10, which in lowest terms is 2 divided by 5. So it means that 7 naught 3 is equal to 2 over 5. Now, the most important thing that you have to take note as far as binary operators are concerned is the fact that a binary operator is not necessarily an operator where you can change the order. You must be very, very careful as to how exactly you were given the binary operator. For instance, C naught D. C came first, D came second. C naught D. So the one that came first is the one that came here minus the second value divided by the first value plus the second value. C naught D is not the same thing as D naught C. The order is very, very important. So whenever you are putting in your values, you must put those values with respect to the order of precedence. We call it order of precedence. You must be very, very careful about this. In advanced classes, you would hear that the binary operator is not necessarily commutative. But that is an advanced term. So let's use what we are very, very familiar with. C naught D is not the same thing as D naught C. Let's see. You are given 7 naught 3 to look for. If you now decided to say, okay, the order does not matter, let me do 3 naught 7, I'll still get the same thing. Let's see what happens. The moment you do 3 not 7, if you were to compare to C not D, what would that mean? It will mean that 3 would now take the position of C and 7 must now take the position of D, which means that 3 not 7 will be the same thing as 3 minus 7 divided by 3 plus 7. And this will give you minus 4 divided by 10, which in lowest terms is minus 2 over 5. So you see that the answer is not the same. The order of precedence is very, very important. Whenever you are given the values, whatever is on the first side will compare to the first side of that value and will immediately enter its pattern within that definition. You are not allowed to change that pattern of the definition, because the definition is what guides that binary operation and what makes the binary operator exist in the first place. Without the definition, not is just a single symbol not. It has no significance as far as calculation is concerned. What gives not the importance is this definition for it. So the order in which the definition is given to you is very, very important. Let's take another one. Let's say you want to take, let triangle be a binary operator defined by a triangle B is equal to a raised to the power of B divided by AB. Let's see this. If you have this as your answer, let's now look for 2 triangle 3. The very first thing is you have to compare the order of precedence. 2 triangle 3 implies that A is in fact 2 by comparison first, and B, which is second, is 3. So if this is the case, 2 triangle 3 will now be equal to what? A, which is 2, raised to the power of B, which is 3, divided by what? A times B, which is what? 2 times 3. And this will give you what? 2 raised to the power 3 is 8 divided by 6. And if you were to cut this in lowest terms, you'd have this as 4 over 3. Now, see what happens if you decided to do it as 3 triangle 2. In this case, it will mean that A will be equal to 3 and B will be equal to 2. Order of precedence. And then what will that happen? You'd have this as A raised to the power of 3, 3 raised to the power of 2 divided by what? 3 times 2. And now, this would be what? 3 raised to the power 2 will be 9 divided by what? 3 times 2, 6. And then if you were to call this in lowest terms, you'd have this to be 3 over 2. So the order is very, very important. You must ensure that whatever you are doing, as far as binary operation is concerned, your first focus is to ensure that you are not using the definitions in a wrong form. Now that we have a very good background as far as binary operation is concerned, we will now move on into 2 very important concepts as far as binary operation is concerned. 2 very important values that are as important to binary operations as they are the normal operators we know. For instance, the 2 concepts we'll be talking about, we would also look at their equivalent values as far as the arithmetic operators are concerned. We will now look at the fact that those arithmetic operators and the values we know for those arithmetic operators, these concepts we'll be talking about in terms of the binary operators will now be the generalization of those concepts in the arithmetic form. Let's get to that. So let's make do with this side first. Now, as mentioned, we are going to be talking about those 2 concepts that make binary operations what they are, as well as the equivalent forms in the normal arithmetic operations. So let's start with the arithmetic operations themselves. For instance, do not forget that in plus, we have some terms we call the additive identity and the additive inverse. We have the additive identity and the additive inverse. Recall that we say that the additive identity is that term that if you add it to any other number, you will get that number back. And The additive identity, in fact, is the number 0, such that if you were to take 5 plus 0, you will still get 5. If you were to take minus 20 plus 0, you will still get what? Minus 20. So we call what? 0 as the what? The additive identity. This would have been covered in a secondary school syllabus, the additive identity. We also talk about another value, which is the additive inverse. We say that the additive inverse is a number that we will add to the original number to get 0. The additive inverse of a number is that number we will add to the original number to get 0. For instance, the additive inverse of 5 is minus 5, because if we take 5 plus minus 5, we will get 0. The additive inverse of minus 20 is 20, because if we add them together, we will get 0. So we'll talk about the fact that minus 5 is the additive inverse of 5, and then we'll say that 20 is the additive inverse of minus 20. These are terms we are very, very familiar with as far as our O-level is concerned. Now, what are the major things we can draw out from this point? We can draw out of the point is that, number one, the additive inverse or the additive identity is 0 for every number you pick. As far as you are in the arithmetic operator plus, the additive identity 0 is true for all the numbers. Even if you take 3 over 2 plus 0, you will still get 3 over 2. Even if you take 30 million plus 0, you will still get what? 30 million. Does that make sense? The next thing we can also notice is that the additive inverse changes for each number. It is a specific inverse for each number. What does that mean? It means that if you are looking for the additive inverse of 5, which is minus 5, it is different from what you will have when you are looking for the additive inverse of minus 20. Just as the additive inverse of minus 20 is 20, the additive inverse of 20 itself is minus 20. The additive inverse of 1 million is minus 1 million. The additive inverse of minus 3 over 2 is 3 over 2. Which means that for each number, you have a unique additive inverse. And for all the numbers, you have one additive identity. Does that make sense? It means that the identity is general for all of them and the inverse is specific. Of course, the same concept holds true for your multiplication as well. For your multiplication, when you take 5 times 1, you have 5. If you take 3 over 2 times 1, you will still have what? 3 over 2. 1 is the multiplicative identity. The multiplicative identity. That is, 1 is that value that if you were to multiply every other number by 1, you will get that number back. Similarly, we can find what we call multiplicative inverse. That is, what is that other number that if I multiply with the original number, I will get 1. For 5, the multiplicative inverse of 5 is 1 over 5. If we multiply them together, we have 1. The multiplicative inverse of 3 over 2 is what? 2 over 3. If you multiply them together, you have 1. The multiplicative inverse of minus 20 is what? Minus 1 over 20. If you multiply it together, you will have 1. What does that mean? It also means that the multiplicative inverse is unique for each number you pick. This is a very, very important concept. The identity is the same for all the numbers within that operator. The inverse is specific and unique for each number within the operator. These values will now form the premise for our calculations of our journey or foray into the concept of identity and inverse in a binary operation. Now, let's look at it. So we'll now compare this generalized form